Let's start chapter 2.6, which is about implicit differentiation. I want to start with a demo that is related to something we'll see kind of near the end of the implicit differentiation section, but it's just kind of fun. We're going to be using Scratch program. This is not required, but it's nice to link between concepts. So let's suppose that something's going to move using delta x that's proportional to the current y position. So here's the origin, here's my object. It has a positive y position. But its delta x is -1 times y, so its delta x is going to be negative valued. And its delta y is going to be proportional to the current x position, so delta y here is +1 times x. X is positive, so delta y will be positive, but delta x is negative, so it's going to take its first step that way. So here both y and x are changing with time rather than y being a function of x. So it's going to take a step in this direction to start with. Let's switch to our demonstration. All right, here we are in Scratch, and it's got the same formulas, but here this b is -1, like we just said on the paper. And I'm going to hit play, and we'll see what happens. So at this point, stop and think. What's going to keep happening? Sorry, it's a little blurry, but those square boxes are object, and the arrow is showing what direction it's pointing in, where it's going to move next. Okay, make your prediction about what's going to happen. Ready? Here we go. Maybe you didn't expect that, but now you can kind of predict what's going to happen. So I kind of knew that was going to happen when we first did it. And let's go see inside. Let's zoom out a little bit. So we can also erase the whole thing, start there again, but I'm going to run a slightly different block of code this time and see what happens. I guess I forgot to put the pen down, huh? All right, let's try it again with the pen down. Oh, rainbow this time. But this time it didn't spiral, it just connected back with itself. So it turns out the difference is, and let's switch back to the paper. So the difference is for circling versus spiraling. Here you can compute delta x, and then you could use that to update x. And then with your updated x, do you use that to compute delta y? Or do you compute delta x and delta y first, then update x, and then update y? And that makes a difference between circling and spiraling. Another thing that implicit functions are related to, or implicit differentiation is related to. So implicit differentiation is differentiation of implicit functions. And then what's an implicit function? Differentiation of implicit functions. So what's an implicit function? It's a function that isn't defined in our usual way. It says, here's an equation that x and y satisfy, but without saying, here's how to compute y from x. Or vice versa. So from a pure math point of view, you might have something like x cubed y to the 8th plus 29x to the 1.7 y to the 11 plus 15x to the -2 y to the 3 equals 120. You can see how that would be a pain in the neck to solve for x in terms of y or vice versa, right? Where do we ever see these? Well, they are useful in pure math, and the unit circle is also like that. In economics, they do something like this for substitution effects. For example, if you go to a store and they're out of your favorite thing, but there's this other product like it, sometimes you just buy that other thing, the thing like your favorite, and sometimes you just don't bother. Maybe it's too pricey, maybe it's not the right flavor or whatever. You can also see this happening in blood types. Um, from what I understand, anyone can receive type O blood, even if you're type B blood person, but it can't always go backwards. And so if the hospital has a lot of type B blood on hand, they'll use a lot of it and not very much of the O for that for type B people. But if they have less on hand, then they're going to be using more type O as kind of a substitute for the type B. And the formula that economists usually use for something like this is alpha times x to the p plus 1 minus alpha times y to the p to the 1 over p is constant. It turns out you can solve that for x in terms of y or vice versa, but they like to think of it this way. Let me show another related thing in Desmos. All right, this is a problem that's related to optimizing the behavior of an industrial system. We've got this function u times minus log x minus log y minus log 3x plus 5y plus 15, blah, blah, blah. And this contour here is all the points xy that make that function equal to 1, I think, or not, equal to 19. And I can grab this point and say, okay, all the points on this shape make the function equal to 20.95, etc. So we've got all these different contours. Maybe you didn't expect it to have that shape. And we can show all of them at once, if we're lucky here. There we go. And we might be asking, so this blue line says kind of which way to go to get larger costs the quickest, or if you go the other direction, to get smaller costs, and it's perpendicular to this contour. You could also imagine a tangent line to this contour, and that's more what we're going to be doing for implicit differentiation. So why are we doing this in Calc 1 when there's all that fancy stuff? Well, it lets us differentiate log functions and inverse trig functions. Basically, log is the inverse of exponential, so it's another kind of inverse. And we'll be using implicit differentiation in Chapter 4's related rates section. So let's launch into a small problem.